Hi everyone, this is Professor Oaks, and in this video we are going to talk about section 2.8 one-to-one functions and their inverses. And so the inverse of a function is a rule that acts on the output of the function produces the corresponding input. So the inverse undoes or reverses what the function has done. So some of the functions that we will talk about have inverses and some of them will not, and the ones that do are called one-to-one. So here's the precise definition of a one-to-one function, and you can see it here that a function with a domain A is called a one-to-one function if no two elements of A have the same image. That is, f of x1 does not equal f of x2 whenever x1 does not equal x2. So determine whether each of these functions right here, f and g, is one-to-one, and if it is not one-to-one, explain why. All right, so if I look at this here, 4 maps to 10, 3 maps to 7, 2 maps to 4, and 1 maps to 2. Now, here I see that 4 maps to 10, 3 maps to 4, but 2 also maps to 4. So that means that these two x values, or values in set A, because we usually call these the x values, have the same value that they map to, or the same image. So in other words, you can think of the set A as being all the pre-images, or generally the set where the domain is going to come from, and B as being all the images, so pre-images and images. And so then that means that this function g is not 1-to-1 because the elements of A, meaning 2 and 3 in this case, have the same image, and that image was 4. All right, but in function f, there are no values in set A, or no elements in set A that have the same value in, or map to the same value in set B, or have the same image. So f is 1-to-1. So hopefully that clears up, again, this definition and how it will look visually, that you don't want any of the elements in set A, the set of pre-images, to have the same image. So that means that these two y values should not be equal, but here we have two y values that are equal when g of 3 is equal to 4 and g of 2 is also equal to 4. All right. So another way to look at this visually is through the horizontal line test. And this is a geometric test for determining whether a function is one-to-one. And it says that a function is one-to-one if and only if no horizontal line intersects the graph more than once. But you can see here that here we have f of x1. So this is x1 f of x1. And here we have x2. So this is x2 f of x2. So here we have that, well, f of x1 equals f of x2. and x1 is not equal to x2. So that means that these two y values should actually not be the same if the function is to be 1-to-1. So therefore, f of x is not 1-to-1. So we can tell this again by just drawing a horizontal line. Now, by the way, to go back to this, if I did something like this here, it shouldn't be that hard to do. We have 1, 2, 3, 4 is the pre-images, and then 4 mapped to 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 3 mapped to 4, so 3, 4, and 2 mapped to 4, and 1 mapped to 2, but you can see that the same principle applied here, that again we could draw a horizontal line and see that two of the values had the same y value. So this is the same principle, but this was drawing it as a arrow diagram, and this was drawing it as a graph. All right, so use the definition of a one-to-one function to determine whether f is 1, and that should say 1, 2, 1 here. So graph f to demonstrate the validity of the result. So that means that we need to find f of x1, which is 3x1 minus 2, and f of x2, which is 3x2 minus 2, and see what happens when these are equal. All right, so if we do that, then we will add the 2 to each side. So 3x1 equals 3x2, and then divide by 3 on each side. So we have x1 is equal to x2. So if x1 is equal to x2, then f is 1-to-1. Now, if we use a graph to verify this, this is actually a line, and it has a slope of 3 and a y-intercept of -2. So here is -2, and the slope is 3. So up 3, right 1, up 3, right 1. And you can see that the graph of this line passes the horizontal line test. Now, let's try this one here, part B. We have 2x1 squared plus 1 equals 2x2 squared plus 1. So same thing, substitute in x1 and x2, set these two equal to each other, subtract 1 on each side to get 2x1 squared equals 2x2 squared, divide by 2 on each side to get x1 squared equals x2 squared. Then we will take the square root on each side. So x1 is equal to plus or minus the square root of x2. Remember that there are two solutions here. Again, another way, if you don't remember to put the plus or minus, is to subtract the x2 squared, then factor x1 plus x2, x1 minus x2, because it's a difference of perfect squares, and then set each factor equal to 0, and you will see that x1 is negative x2 or x1 is x2. So that means that there are two solutions and not one. So f, or whatever the name of this function is, because it didn't say, but that's okay. I'll just call it f. F is not 1-to-1, but I know that if I draw the graph of 2x squared plus 1, it has a y-intercept of 1, and it's a parabola opening upward, and I can see right away that this graph does not pass the horizontal line test. So that's another way to show that this function is not 1-to-1. All right, so in example 4, we'll just use the horizontal line test to determine or decide whether each function has an inverse. But these graphs are already given for us. Here, I already know that this is a parabola, and so a parabola is not going to pass the horizontal line test here, and so this is not 1-to-1. But here I have in part B a line, and this line does pass the horizontal line test, so this is 1-to-1. All right, so here is the definition of an inverse. So if f is a 1-to-1 function with domain A and range B, then its inverse function, and this is not the reciprocal or f to the -1, that's just the notation for an inverse function, has domain B and range A, and is defined by f inverse of y equals x, and this is if and only if f of x equals y for any y in B. So again, here's the A, this is the domain, this is again the set of the pre-images, and then the set B will be the domain, or the range, and these are all of the images over here. So to get from x to y, we use f, and to get from y back to x, we use f inverse. So consider a 1-to-1 function f from R to R. So this is from the real numbers to the real numbers. All this means is that the numbers in the domain have to be real numbers, and then all the numbers over here would be real numbers. So it means that you can't get, say, a real number here and then have an imaginary number over here. That's all that means. It's just saying that if you have a real number over here, you want a real number over here. All right, so this is a real number to a real number. So f of 1 equals 5. So here is the A and the B, and here is the 1. If f of 1 is 5, so we use f to get that, then f inverse of 5, to go back to that, 5 back, we would get 1. So f inverse of 5 is 1. So the same thing here for part B. If f of 3 is 7, and 7 maps to, 3 maps to 7, and then 7 maps back to 3, so f inverse, then I know that f inverse of 7 will be 3. All right, and same thing for C. Now, C is a little bit different because they're telling you to go from f inverse of 3, you get a -1. So if I want to go from -1 back to the 3, then I use f. So f of -1 will be 3. Hopefully you see how that works now that C was flipped around, but I use the same idea here. So the inverse function property, I'll let f be a 1-to-1 function with domain A and range B. The inverse function f inverse, again written with the -1 symbol, satisfies the following cancellation properties. F inverse of f of x equals x for every x in A, and f of f inverse of x equals x for every x in B. So again, this is another way of writing this f of f inverse of f of x, and f of f inverse of x. But again, if these both equal x, then f and f inverse are indeed inverses of each other. So if I want to verify that x to the third and the cube root of x are inverses of each other, then I can just verify that f of g of x equals f of g of x has to equal x. So that's f of, I'll substitute the cube root of x into f here. And if I do that, I have the cube root of x to the third power, which those cancel out, and that will give me x. And now I have to also verify that the other way is true as well. So g of f of x, so g of f of x, so that would be substituting the f into g, so g of x to the third. So we have the cube root of x to the third, which is also x. So it doesn't matter if we take the cube root and cube a number, or cube a number and then take the cube root. We will start realizing we'll get the same number that we started with back. All right, so that's what it means to be an inverse. So let's verify that f of x is 2x plus 3 and g of x is 1/2 x minus 3 are inverses of each other. So again, we need to verify that f of g of x equals x, and g of f of x also equals x. So f of g of x, if I substitute g of x into f of x, I have f of 1/2 x minus 3. I'll substitute that again into f. So I'll put this in parentheses as 2 times 1/2 x minus 3 plus 3. 2 times 1/2 is 1. So I just have x minus 3, or 1 times x minus 3 plus 3. Negative 3 plus 3, 0 out, and I'm left with x, which is what I'm supposed to get if these are indeed inverses of each other. Now g of f of x, that's g of f of x. So I'll substitute the f of x into g of x, so g of 2x plus 3. Then I have, all right, let's do this, 1/2 times, I'll put the 2x plus 3 in parentheses just to make sure that I'm doing this correctly. The 3, 0 out, and 1/2 times 2x, 1/2 times 2 is 1, so I have x left over, or 1x. So since these are both x, that means that f of x and g of x are inverses of each other. All right, so it asked us here in the problem to verify that, and that's what we just did. So now let's verify that the inverse of f of x equals 3 over x plus 5 is f inverse of x equal 3 over x minus 5. So f of f inverse of x and f inverse of f of x both have to equal x. All right, so let's do this. So f of f inverse of x, I'll substitute f inverse of x into f of x. So I have f of 3 over x minus 5, which gives me 3 over x minus 5 plus 5. The 5's 0 out, and I'm left with 3 over x. I'll multiply by the reciprocal to get 3 times x over 3. The 3's divide out, and I get x. Here, I have f inverse of f of x. I have f inverse of f of x. And what I'll do is I'll substitute f of x into f inverse of x. So f of x was 3 over x plus 5. And then I'm left with 3 over x plus 5 minus 5. I'll multiply by the reciprocal here. 3 times x plus 5 over 3 minus 5. The 3's divide out. Now the 5's 0 out, and I'm left with x. So these are both x, so therefore f of x is the inverse of f inverse of x, or the other way around, f inverse of x is the inverse of f of x. Either way is okay to say that because they're inverses. All right, so hopefully that all makes sense now. So now that we've practiced verifying the inverses, there we're going to actually find the inverses. So here are some steps to help you do that. Write y equals f of x, then solve the equation for x in terms of y, if possible, and then interchange x and y in the resulting equation of y equals f inverse of x. So graph f inverse of x and f on the same coordinate system, and then what you know is about the graphs of f inverse. So after we find the inverse, f inverse of x, we'll graph these and see what we notice. All right, so here we go. So write y equals f of x. So step 1 is instead of f of x equals 2x plus 6 over 3, we'll have y equals 2x plus 6 over 3. Then step 2, we'll solve this for x in terms of y. So here's x. So I need to solve x. All right, so multiply by 3. So 3y is 2x plus 6. I still have x over here, so I'll subtract the 6. 3y minus 6 is 2x. And then I'll divide by 2. So 3y minus 6 over 2 is x. And then I'll interchange the x and the y. So interchange the x and the y. So that means that 3x minus 6 over 2 is y, or f inverse of x is 3x minus 6 over 2. All right, so now remember that another way to write f of x is 2x over 3, or 2/3 x plus 6 over 3 is 2. And another way to write f inverse of x is 3x over 2, or 3 over 2x minus 6 over 2, which is 3. And I'm doing this so that I can graph these more easily by realizing this is a line with a slope of 2 over 3 and a y-intercept of 2. So I have a y-intercept of 2, and then I go up 2 and right 3, up 2, right 3. All right. So now there is f of x. All right, now for f inverse of x, I notice it has a slope of 3 over 2 and a y-intercept of negative 3. So here's negative 3, and a slope of 3 over 2 means up 3, right 2, up 3, right 2, up 3, up 3, right 2. All right, so here we go. All right, now hopefully you can see that at some point these are going to intersect. All right, so you could figure out where that is going to be fairly easily. So how would you figure out where they are going to intersect? Just set them equal to each other. 2/3 x plus 2 equals 3 over 2x minus 3. Then I'll clear the fraction by multiplying by 6, 6, 6, 6 to get, well, 4x plus 12 equals 9x minus 18. Then subtract the 5x to get 12 is 9 minus 4. So minus 4x. 9 minus 4 is 5, so 12 is 5x minus 18. Add the 18, so 12 plus 18 is 30, equal 5x, and divide by 5, so x is 6. All right, so they're going to intersect at 6 and 6. So that's well, my I've told you that my my graphing isn't going to necessarily be the best, but here we are. This is f inverse of x, and what hopefully you notice is that these are going to be reflections about the line y equals x. All right, so here y equals x, and these are reflections over the line y equals x. Let's try another one. All right, so f of x is x over 2x plus 1. Step 1 to find the inverse is to write y equals f of x. Then we'll solve for x. So here's x and x. So step 2, we'll multiply by 2x plus 1. So that's y times 2x plus 1 equals x. I'll distribute here. So 2xy plus y equals x. I'll subtract the y to get 2xy is equal to x minus y. I'll add the I'll add the oh boy, well maybe I wouldn't do it that way. I'll just subtract the x. That will make it easier for all of you. So 2xy minus x equals negative y. Factor out the x, so x times 2y minus 1 is negative y, or the opposite of y, and then divide by 2y minus 1. So we have x is equal to negative y over 2y minus 1, and then step 3 is to just interchange the x's and the y. So the x's and the y's change spots. So we have y is negative x over 2x minus 1, or we can write it f inverse of x is the opposite of x over 2x minus 1. Now, all we're going to do is graph each of these functions here. All right, so I know for f of x, 2x plus 1 cannot equal 0, so 2x cannot equal negative 1. And if I divide by 2, x cannot equal negative 1/2. So here is a negative 1/2 here, and x cannot equal a negative 1/2. And then also, I know that I have not talked about this necessarily in the class yet, but here's the first time that I'll mention this. If I look at the ratio of the highest power terms in the numerator and denominator, x over 2x, that will be a half, then that will give me the value of a horizontal asymptote value that the graph cannot approach. And then from there, you can pick a couple of points on the graph, such as say if you have x is 0, you have 0 over, well, I hope that you can see that 0 over 2 times 0 plus 1 would give you 0. So 0, 0 is a point on the graph, and then you can pick a lot of other points, like negative 1 would give you negative 1 over 2 times negative 1 plus 1. That will give you a positive 1. So 1 is another point on the graph. And then if you fill in enough points, you'll realize that the graph looks something like this. All right, now for the inverse, something similar. The denominator 2x minus 1 cannot equal 0. So if you add the 1, 2x cannot equal 1, and x cannot equal a half. So x cannot equal a half. and then the ratio of the highest power terms in the numerator and denominator will be a negative a half. So here is a y asymptote, like a horizontal asymptote at y equals negative a half. And then you can plot a few points very similarly to this and realize that this particular graph looks like this. All right, so here we go. All right, so well now. Oh, by the way, yeah, this is actually uh, something where you could figure out a whole bunch of points if you wanted to, but again, it's not really necessary. But you can hopefully see again the reflection over the line y equals x. So I won't necessarily make you graph the graph of f and its inverse every time because as you can see, this gets pretty messy. But it's important to see what happens once in a while at least. All right, example 10. Let f of x equals x squared minus 2 and g of x equals x squared minus 2 when x is greater than or equal to 0. Use the graphs of f and g to explain why f does not have an inverse and g does have an inverse. Find g inverse of x. So f of x equals x squared minus 2. This has a y-intercept of negative 2, and it is a parabola opening upward, so it looks like this. And of course, this graph of f does not pass the horizontal line test, so does not pass the horizontal line test. So therefore, f of x does not have an inverse. But g of x equals x squared minus 2. If we only draw the part of the graph that is greater than or equal to 0, then this is what we have. Excuse that point right there, but it's only the part of the graph where x is greater than or equal to 0. So only this part of the graph. So this actually does pass the horizontal line test. So passes the horizontal line test. And now we can find the inverse. And step 1 is changing this to y equals x squared minus 2. Step 2 would be solving for x. So let's add the 2, and then we'll take the square root. So square root of y plus 2 is equal to x, but we don't need plus or minus because x was greater than or equal to 0. So that's why we only get one answer here and not 2, and why it therefore does have a function that's an inverse. All right, so, or it does have an inverse function. Now, then we write step 3, which is just interchanging the x's and the y's. So the square root of x plus 2 is y, or f inverse of x is equal to square root of x plus 2. All right. Hopefully that all made some sort of sense now. And the same thing here, I'm going to repeat myself about the graphical representation of the inverse. The graphs of f and f inverse are reflections of each other about the line y equals x. So now, if I look at this, use the graph of f given below to sketch the graph of f inverse and identify the domain and range of f and f inverse. Well, if I just want to reflect over the line y equals x, which is already written here, or drawn here, then that should be pretty easily done. It should just go something like this. All right. So now, what is the domain of f? Well, I know the domain of f looks like it's going to be any real number, negative infinity to infinity. Uh-oh. Yes. And then I know that the range of f will be only numbers 0 and higher. So this is actually, you know what? This I told you my drawings are really. I told you my drawings are really that bad. I'm I know my drawings are that bad, but I'll show you what happened here in a second. But you can see that this f is not actually going anywhere below 0, and so then the domain of f inverse will actually be the range of f. So I know that should be 0 to infinity, and the domain of f is the range of f inverse, so that should be negative infinity to infinity. So I knew that I jumped the gun here a little bit on like drawing just drawing a line here that really didn't make too much sense here, and that this will look more like if I'm honest about it, something more like this. All right. All right. So if I just draw random lines, yes, I will get in trouble. But then again, you see that my double check on this to make sure that I didn't just accidentally draw a random line and get in trouble for it later was to double check that the domain of f should be the range of f inverse, and the range of f should be the domain of f inverse. So now, if I want to go ahead and do this again, all right, so if I want to go ahead and do this again, remember sort of what is happening is that you want the if you want to do a reflection over y equals x, that the xy actually becomes negative y, negative x. All right, so even my graph here was, again, just a sketch. If I want to be more accurate, I could be more accurate, but I don't even know what this exact value is where it intersected the y-axis, so I'm not concerned much about that. But that means that this negative 2, negative 1 becomes, all right, so I need to make the new x value the opposite of y. So 1, 2, the negative 1, 0 becomes 0, 1, following the pattern of changing x, y to negative y, negative x. And then 2, 1 becomes negative 1, negative 2. So 1, 2 is 1, 2 is here. All right, 0, 1 is here. And negative 1, negative 2 is here. And then you can see that this was indeed, hopefully, you can see that this is indeed a reflection over the line y equals x. This one might not be as easy to see, but hopefully you can see the general idea. And this is why, again, I'll just make you sketch these. But here, the domain of, and I'll label that f inverse, and this one f inverse, and this one was f. So the domain of f was from a negative 2 to 2, and the range of f is from -1 to 1, the y values and the x values, all right? And then we switch these around, so the domain of f becomes the range of f inverse, so that is -2 to 2, and the range of f becomes the domain of f inverse, so that is -1 to 1. So you can see that the f inverse did go from -1 to just 1 now, and then the range of f inverse that f the y values of f did go from the -2 to 2. All right, so there you go. So that's maybe a slightly more complicated example of finding the graph of an inverse than you really need to know about all the time, but it's an example. So again, I'm not going to do the application problems of inverse functions today, but if you want to do that on your own and you enjoy doing that type of thing, feel free to do that. So what a time to be alive, and I will hopefully catch you in the next video. Have a nice day.